So maybe we should begin. Well, so we have a second lecture by Nigel. So take it away, Nigel.
Great. Okay. Thanks a lot. So yeah, so I just put up the slide that I finished with last time, just to recap what I covered in the first lecture.
Well, so we have a second lecture by Nigel.
Yeah. Okay. So there, I made a start on introducing topological band theory by focusing on one-dimensional systems and showing how we can introduce this. We could use the Zach phase in circumstances where there is a symmetry, a chiral symmetry, which applies for this Schrieffer-Heeger model within the type binding limit and that we discussed, such that the Zach phase can be pi times an integer, and that integer can be used to characterize topological properties, and in particular, if there's a boundary between two regions of different, where the Zach phase changes by pi, then there's a topological zero energy state, and this is topologically protected, meaning it's exactly at zero energy, provided you, the only perturbations you introduce preserve the symmetry. That is, that they anti-commute with this sigma z operator that was shown there. But there was one aspect that I wanted to cover, but I didn't. But I want to do quickly, which is to take this solution. So I told you what the solution was for the sharp terminated SSH chain, this semi-infinite chain, where we just suddenly to the left, the coupling J falls to zero, and we have this exact solution, which is exactly at zero energy. And I wanted to show that, well, we've argued that that's robust to changing the model as long as you preserve the symmetry. And one way in which we can modify the model is to go to the other limit, instead of having an abrupt change, to having a very smooth change in the parameters. So here I want to just sketch what the continuum theory is for this edge state. And for this, what we're going to say is that we'll let some quantity I call m of x, which is defined to be 1 minus j prime over j, very smoothly with position x. So this is to represent a transition as a function of x between the non-topological and topological regions. So we have m of x, and for our convention, the non-topological was when j prime was greater than j, and so far to the left, we're going to have m minus far to the left and m plus far to the right. So this is the region which is non-topological, and this is a region which is topological. And so, of course, at the point x equals 0, well, at the point x equals 0, we set j prime over j equal to 1, so m is 0. So that's the point at which there's a gap closing. Because remember that the gap of the SSH model closed whenever j prime equaled j. And so what one can do is to treat this semi-classically and expand the Hamiltonian around that gap closing point. It closes at a wave vector of pi over a. So actually we need to expand the Hamiltonian h of q around qa is equal to pi. So we write that. So let's write qa equal to pi plus q tilde a. So q tilde a is small. And if we do that, then the Hamiltonian HQ in units of j is approximately this q tilde a times sigma y plus this m of x times sigma x. And in our semi-classical description, then we can view this QA. We can let, everything's changing smoothly in space. We can just think about a solution where QA means the local rate of change, so or Q tilde means the local rate of change of the function, like in a WKB approximation. So we can rewrite this as minus IA d by dx. So I'm replacing Q tilde by minus d by dx, and then I have sigma y plus m of x, sigma x. And this gets us to a one-dimensional model, which is a famous model due to Jackie van Rebbe from 1976. And what you can show, and I won't do it here, but I leave it as an exercise to check that there's an exact zero energy state, provided there's a change from negative to positive n plus as written, there's a normalizable zero energy state psi, which I can write as e to the minus the integral from 0 to x of m of x prime dx prime over a e to the I pi x over a and 0. So this is the continuum version. You can compare with the lattice version I showed before here, where we have something that's it's an eigenstate of sigma z. It only has amplitude on the a sites, and if j prime is j prime is less than j, then it's normalizable. It's decaying, and here this will decay provided m is positive. That is, we're in the topological phase. So this is just another viewpoint far from the abrupt limit, where we can see that there's an exact zero energy solution when we have this chiral symmetry.
So Nigel, can I ask a question here? If I go to this limit where the domain wall is varying really slowly in space, or the order parameter, this function varying really slowly in space, does this exact zero energy state get embedded in a continuum of other states? Just because I would expect locally there would be some gap states, but of course that gap's closing, and so all around that point where the gap closes exactly, there should be some really low energy states.
So indeed, there could be some. I mean, the gap. Indeed, the gap is getting small. So indeed, there could be some other non-universal subgap states in any. There's no reason why we can't have a state at the edge of the band that would come in. So I think that's definitely a possibility. I don't know if I haven't thought through it, or I don't know of an explicit calculation of how those states collapse, or in which models they exist and how those states collapse. But I think you're right that one would naturally anticipate that as well as this exact zero mode, that there could be some non-topological subgap states as well, which are. And subgap, of course, meaning less. I mean, there's a bulk gap. When n plus is very, when you go very far from it, and at this n plus in the asymptotic value out here, if we take that as our measure of the gap, then there are certainly likely to be other states at lower energies inside.
Yeah, and I guess the subtle thing in my mind is just that as you make this smoother and smoother, as you make this more and more semi-classically applicable, that presumably you get more and more subgap states, and they get closer and closer to zero energy, right? So there might be some background continuum that it's embedded in.
I think that's true in the limit. I mean, one can still make a semi-classical approximation and have quantization. I mean, by that argument, you'd also say the simple harmonic oscillator is a continuum. But we know that we can do a WKB approximation and get n, and even n plus a half, and we're okay with the fact that the semi-classical approximation will accurately give you the level spacing. Now, the level spacing will get smaller and smaller as we go more into the semi-classical limit, but it's still giving a valid quantization and differentiation between the different quantized levels. So I don't see it as a flaw or problem with the semi-classical limit. I think that can still cope with it, but it is a feature of the model and the physics of that very broad domain world. That's true. Yeah. Thanks.
I mean, one reason I ask is for detecting it in a lot of these cold atom systems, we have traps and things. And so if I have a peak, but there are a bunch of other states laying around, how do I differentiate one robust level with a bunch of levels around? Anyway, but thank you. That was very clear.
I think you're absolutely right. And I think that, just seeing a state at the edge is not by itself clearly topological. The topological aspect is that it's at zero. Its energy is pinned in the middle of the gap, and it's robust to perturbation. So I think that just seeing a state, it's not everything, but seeing its robustness and its energy is.
So Nigel, I mean, wouldn't you say, like, if you forget, sort of realistic system in the sense of maybe having disorder, trap, whatever, and really just focus on the idealized model you analyzed, SSH model, and look at the continuum, I don't think, as far as I understand, there are no other states. This is the only state within that model that's going through the, that's because M variation, the gap, M variation is localized only in a small region or in some region, then this is the only solution, as far as I understand, that is in a mid gap, that's at zero energy. The rest of the states, the bulk states are robustly gapped by M plot, magnitude of M. Isn't that true?
There's a I think that, so I mean, you have to look in. So if we take the bulk to be somewhere out here, then there's definitely a gap of gap by this M, whatever M asymptotes to.
Exactly. Yeah.
But I think Caden's point is that, and that that gap, that gap, of course, is sort of it's the magnitude of M. So that gap is sort of falling and then coming up again, right? And so if I just sort of plot if I just plot the gap, as a function of position, taking the strict kind of semi-classical, just the local limit where I don't worry about any quantum motion, just saying that at this point, what is the gap? Then it looks like this. So it does look like a potential well. And I think Caden's point is, well, couldn't we have some state that sits here? So we can have a state that lies at this energy, which let's say there is such a state. If it's not below the gap here, I can always make my gap outside as big as I want to make it bigger than any bound state that I happen to find here. Mm-hmm. And I think that I don't think that I can't rule out the existence of such states for any model or any variation of M of X. I don't see how to rule it out. But what we've shown is that there's one exactly at zero. That's for sure, but we haven't shown that there aren't any others. And I think that my intuition would be that there probably are some others in some reasonable.
But isn't the solution to this continuum, Jacobi equation, at non-zero energy, if you look for all the solutions, isn't that a way to answer that question?
It would be. Yes, that's right.
I think it's contained in everything you've written down within the semi-classical, WKB-like approximation, as long as MX is varying smoothly.
Yeah. So indeed, I'm sorry, I don't know the answer. I'm just saying I can't say they don't exist.
Okay, you're being very conservative, but I'm trying to be less conservative. But anyway, that's
a good thing to look into, to see if there is a particular reason in this model or exact result that there are no other subgap states. That's an interesting question. I don't know the answer. I wish I did.
So related to this, more for pedagogical reasons, you have a little bit of space to the right of your figure. Can you write down, just for the reference, the discrete model from which your continuum QA sigma y Hamiltonian comes from? Just so because I don't recall there was a sigma y there, and so just would be nice.
So it was. Let me see. So we had HQ was, remember, 0, 0, J prime.
Oh, I see.
J e to the I Q A.
Okay, there's a sine and a cosine. I see.
Yeah, that's right. So
Okay.
so then we'll have so then we'll have that HX is J prime plus J cosine QA, and HY is J prime minus I J. Sorry,
Okay.
minus J. No, there's no J prime. Sorry, let me just get it. Is HY is J sine QA.
So it's just the expansion of Q of the sine. Okay.
Yeah. So sorry, there's no tilde in that. That's QA. So so we're So exactly. Have I got sine? Yeah, that's right. Yeah.
Yeah.
No,
So that's. I think that's right. That's the sigma y.
No,
That's
but I wanted. Sorry, this is terrible. I wanted the gap. The gap closes at QA is pi.
Oh.
So I want both of these to gap close when both of these vanish.
Well, J prime equals J.
Yes, right at the J prime and J, then H is going to go to 0 at pi.
That's right.
Exactly. Yeah. One due to sine and one and the other.
Oh yeah. Okay. Yeah.
Yeah.
Okay. Fine. Yeah. Good. Okay. Good. Sorry, I'm just being. Yeah. So it's that, and so we're expanding around this gap closing point, and the gap closes at QA is pi, and so that's why we also expand there.
Yeah. So it's very nice because then I can see, and the Q tilde is the deviation of Q from pi, right?
That's right. And so this e to the I pi x that I put here, that's to put it back in the pi it's to put this pi back into the full solution. And that's really something that's alternating from one unit cell to another, and it's the same as this minus sign. There's a minus sign.
Yeah.
So there's an exact correspondence between the two results.
Yeah. No, very beautiful. Yeah. Thank you.
There's a question in the chat that from Thomas Keeley asking, why are we allowed to expand HQ when the function m of x breaks translation invariance?
So I'm doing. It's really a sort of WKB type approximation. If you where you say that you make an approximation that the wave function it's a function of position. It's a stationary state. It's a function of position. But we'll say that to a first approximation, its phase is advancing like the local momentum or local wave vector coming from at that energy, and that amounts to saying that we'll advance this derivative is basically mimicking that it will locally you have a plane wave whose properties are defined by the h of q, but we're going to raise that to something which is varying slowly in space and just replace the q by the derivative. Now, indeed, I haven't proved that. I'm just motivating it. I don't have the clarity of notes to be able to go through it now to explain it, but it's really conceptually like this WKB approximation. I hope that at least gives some qualitative explanation. Okay.
Thank you.
Okay. So okay. Well, that was a to tie up one end, but I see. Well, I'm glad we talked it through. But it's now I want to start the new stuff, which is about the churn bands, and I just and then I'll talk. Try and say something about topological insulators and superconductors and the rule of symmetries there, and something with strong interactions. But we'll see how it goes, and if we don't cover it today, we can cover it tomorrow. So just to put up, this is a slide from last time reminding you about the Berry phase and how we write this geometric or Berry phase in terms of a Berry connection or a Berry curvature. And in the last lecture, what I did was to, well, I said that for whenever we're characterizing the topology of block bands, so for topological bands, we were going to use that this generic parameter x that was appearing here in our Berry calculation. We're going to replace by the wave vector q, and our state psi of x that we're thinking about is our block state un of q, block state, and then we would get a Berry connection in reciprocal space in wave vector, which is I times the overlap of u n of q with the derivative with respect to q of u q of n. And last time, so in 1D, we said that we could construct a topological invariant, at least if there was a symmetry constraint in terms of the Zach phase, just integrating this Berry connection across the Brillouin zone, across the full band. And in 2D, the prescription to get topology, or one topological invariant that appears, is the Chern number. And the way you compute that is by integrating not the Berry connection, but the Berry curvature over the full Brillouin zone. So it's actually 1 over 2 pi times the integral of the derivative, or the curl of AQ dtq. So this was the Berry curvature, which it's derived from the Berry connection. So so this turns out to be a topological invariant and an integer topological invariant for 2D bands. And one thing I want to point out is that you might look at a formula like this and think that that the Chern number should be 0. So just to point out a subtlety here, which is, I think, important just to well, at least to be aware of, and also for the general understanding of what this Chern number represents. Remember that we're computing this integral over the entire Brillouin zone of the curl of AQ, but that's the same as by Stokes' theorem. We could write that as the integral around the boundary of AQ dot dq around the boundary. So just to make it absolutely clear, so if I had some rectangular system with lattice constant AX and AY, then I'd have a Brillouin zone that I can take from minus pi to pi, minus pi to pi, so on. So my Brillouin zone looks like this. And this integral, by this integral around the boundary, what I mean is that we could integrate, take the line integral of this Berry connection along here, then along here, back here, and along that. And because of course that covers the entire Brillouin zone. But if you look at that, you'd say, well, that should be 0, because we have, I have a contribution here running upwards, and then the contribution running downwards at minus pi, and pi and minus pi are the same wave vectors, and similarly at pi and minus pi in QX. So you could say, well, isn't this going to give 0? And the answer is, well, it's not, because the Chern number can be non-zero, but it's a subtlety of, and there's a mathematical feature that you have to be aware of, which is that this vector potential AQ can have point-like singularities which have no physical manifestation, no physical consequence. So it can have point unphysical, point-like singularities. So this is connected to the fact that there's an ambiguity in defining the state at any point in the Brillouin zone up to a phase, and in particular up to a change of phase of 2 pi. So there's an ambiguity, an intrinsic ambiguity in the space of states of this U1 phase. And in particular, we can see that we can make because this vector potential is gauge dependent, meaning if we take, we can take any state we want, UQ, and we can just multiply it by some phase, e to the minus I chi of q times u of q, right? That hasn't changed the energy eigenvalue. I just decided to change the phase at some point in wave vector space, and this causes the Berry connection to change to a q plus the gradient with respect to q of whatever function I put in there. And in particular, I can put in functions which even have just a vortex, where there's I can make a phase vortex which has got where the phase winds by 2 pi around 1 point, and that phase vortex is a singularity which has no physical consequence. This point-like object has no physical consequence, but if we make a line integral of the Berry connection around it, we'll pick up 2 pi. And I could make gauge transformations where if I have something that's periodic, I can make gauge transformations where I add and remove pairs of these vortices. If everything's periodic, I can put in a vortex and anti-vortex, or as many as I want, so I can add and move these around. They have no physical consequence, but what is preserved is the total number of these vortices, and the total number of the vortices need not be 0. It can be that it's non-zero, and the Chern number actually essentially counts the net number of these 2 pi vortices that are in the Brillouin zone. So this is. So I'm really, it's just a, of course, this has got much deeper mathematical foundations, but I'm just giving pointing out an issue if you're working with such problems, that you have to be careful that there's no smooth way in which you can define the vector potential. It will, if there's a non-zero Chern number, there will be at least one point at which there's a singularity in the vector potential, and that is sufficient to account for this fact that you don't get 0 when you integrate around this, because we can shrink that to a loop around this singularity, which has got a certain number of vortices. Okay, so that's a statement of the Chern number and how to that you should be careful when thinking about the vector potential. In this case, the quantization of the Chern number does not require any symmetries whatsoever. This thing must take an integer for any for any band without imposing any symmetries. However, symmetry does enter in another way.
About that last slide.
Of course, please. Yeah.
So you were showing this gauge transformation as a way to demonstrate that integrating around the boundary doesn't have to cancel out on the opposite sides of the Brillouin zone. But this gauge transformation chi q, does that mean that we can have different phases at pi and minus pi? That this chi q does not satisfy like the discrete symmetry of the crystal lattice?
So we could what yes, that's true. Yes, we can impose. We could put in we can put in whatever phase we want at any point in space, but in order to be not to introduce any physical effects, we can only put in singularities which are 2 pi vortices, so that there's some point, there's some point at which the vector potential becomes ill-defined, and as we run around that, the Berry phase that's picked up by that is 2 pi times an integer, and 2 pi times an integer is the same as 0 as far as the overall phase is concerned for any local properties of that region. So there's no problem in making the phase vary in an arbitrary way over the Brillouin zone. So in particular, so I guess the way, sort of crudely, the way that this thing could give you something which is non-zero is to say that there's between, if I take, I have this line which is going to cancel, and it sits on top of it, but just in between, I say that there's some singularity, some vortex singularity, so that whenever I contract this, I'm actually going around some singular point. So I can't just cancel the two without being conscious of the fact that that there can be these singular points, and in particular, it means that in the limit as we approach, let's say the singular point is exactly on the qy = 0 axis, then as we approach it from the left or from the right, then the phase of the wave function indeed differs. It differs by a minus sign. So in a limiting sense, the phases differ at some point in the Brillouin zone, but it's only because that's a singular point, and we're considering the limiting case as we approach the singular point from two sides. But the singular point itself has no physical consequence. It's sometimes referred to as a Dirac string, because Dirac introduced this when thinking about the vector potential around a magnetic monopole, and he used the argument that the singular point there must be some singularity in the vector potential, but in order for that singular point to have no physical consequence, such that the magnetic monopole can be viewed as free from any extended object, it has to have give rise to a phase of 2 pi for electric charges, and this give rise to his beautiful topological argument for why the product of the charge of the magnetic monopole and the electron has to be quantized in order to ensure that these singular points in the vector potential around the magnetic monopole are unphysical and invisible. But it does mean that also there that the vector potential is not uniquely defined over the whole space. There are singular points. In the same way here, the vector potential and the block wave function up to its phase are not necessarily uniquely defined at a point because of this singularity.
Mm-hmm. So I followed most of that. I don't quite understand how we're defining this integral over this kind of funny boundary region. If we view the edges of the Brillouin zone as kind of glued together, then the Brillouin zone itself is like a torus, I guess, in this case. Yes. And in that case, we can integrate the Berry curvature over the full torus. Then this Stokes theorem doesn't apply because there is no boundary of the Brillouin zone. And then this argument doesn't even need to be made.
Yes, that indeed. But so but there one is still one could still break the torus. You could still introduce a surface, two surfaces on the torus. Let me just clear this. So we could still introduce, if this is, think of the torus as a so the Brillouin zone as a torus. We could still choose to, if we want to use Stokes theorem. I mean, and indeed it's not necessarily helpful, but I'm raising this subtlety because sometimes one might try and do it, but you could break it into something where we open it at one surface. And so then using Stokes' theorem, we'll also can relate to the flux to or the integral of the Berry curvature to the integral of this boundary, and there'll be the boundary on the cut, and that boundary on the cut. If you were to try and apply Stokes' theorem, you might say that if Stokes' theorem could be applied, everything was smooth, then you might expect these integrals to cancel on the cut. But all I'm saying is that cannot happen. The difficulty is that there isn't a smooth function A for which you can evaluate the integral of the Berry curvature in that way.
I think maybe it's helpful to like the way you drew the torus and your contour on to the left of it. You can think of it as you go around. It's more obvious that there's something can happen if you go around the single cycle of the torus, which is the first segment of your rectangular path. Then you go around the other cycle. Then you come back and go around the first cycle in reverse, and then finally close the path. So then the curve, although if there were no singularities, they would still cancel, but then it's not as trivial as going around the cycle one way and then immediately reverse, where then it's obviously cancels. You're going around in kind of a non-trivial way. You're going around once around the first cycle, then once around the big cycle, then reverse so I think then the curve is more obviously, non-trivial, and one has to worry about those singularities or vortices that you're talking about.
I think that the message I want to get across, just to sort of draw it back to the message that may be helpful, is that whenever you're computing the Berry curvature, or the Chern number, if you work with the Berry curvature, everything works fine. It's clear. The Berry curvature is gauge invariant up to these transformations that we're talking about. These singularities don't appear at all. And so if you compute the Berry curvature, you're safe to calculate the Chern number. But if you decide that you want to try and get there using the vector potential, or you're trying to construct the vector potential, then you have to be aware of the fact that the vector potential cannot be smooth. It will have, if the Chern number is non-zero, the vector potential will have at least one singular point. So the only message, and that singular point is not a physical point. Now, this was relevant to me at some point in thinking about how you could use spin orbit coupling to try and make magnetic fields in real space, because there was a sense that the vector potential is related to the gradient of the state in real space. And since states change on an optical wavelength, there was sort of an implicit assumption that the vector potential had a maximum value which went like 1 over the wavelength. It turns out that's not true. The Berry curvature has variations that can only change, or the local Berry curvature in real space can only change on the scale of the optical wavelength. But the vector potential that's imprinted by smooth light fields can also have singularities associated, and those are associated like phase singularities or vortices of the light. And so actually thinking in terms of vector potential in that scenario was extremely unhelpful, and you had to, unless you were aware of the fact that there could be these singularities. So the message I want to get across is that is to be aware and to be, that there is a subtlety in dealing with the vector potential, that it can have these Dirac strings.
Excuse me. Oh,
yeah.
Sorry, I have a question. So I know we are considering cases where we have gapped bands, but in graphene, people often talk about this pi Berry phase that they use the vector potential for. And to my understanding, the a Berry curvature is not well defined because it's gapless at one point. So what justifies being able to use one version over the other? So the line integral over the area integral.
So, well, in that case, there is a around the Dirac point, you can construct a uniform vector potential. It has a singularity at the Dirac point itself. So there is a point at which the vector potential and indeed the Berry curvature is singular, and so you should not try and take your integral through that point without being careful in defining it. But in running around the perimeter, there's no singularity or obstruction in constructing the vector potential, so it's entirely smooth in that region. So the differences. Well, that's a one-dimensional problem, or it's a one-dimensional path in a situation which crosses no singular points in and that's the generic situation, I would say. But for the two-dimensional system with some twisted, with this non-zero Chern number, where the integral of the Berry curvature is non-zero, then you're in a special circumstance where the vector potential is where you're forced to encounter the points where the vector potential is non-zero, or it's singular. I'm not sure I can give a generic answer, other than I'm just saying that the two situations are rather different, and so I don't have a more generic response, I'm afraid.
Okay, thanks. I'm sorry, but so are you saying that I could still do a Berry curvature area integral, but in a region that does not include the gapless point? Or are you saying that Berry curvature is...
Well, you need to. So the Berry, in that case, the Berry curvature is a delta function. So one can. So there is. So if you have a path, it's a delta function at some point. If you have a path that doesn't encircle it, then the integral over that area doesn't include, the Berry curvature vanishes outside of this point, and so any loop that doesn't encircle this point will have zero phase accumulated. So
okay.
But if you in the case where you encircle that point, that there is curvature. It's a singular thing. It's like the curvature of a cone. It's a singular point, and the integral of the vector potential around it. The vector potential has no singularity. You'll get some value of pi for the net phase that appeared, but the only way in which you can relate that to a Berry curvature at a point is to say that there was a delta function of weight pi at this point, and when you integrate over the area, you pick up that pi delta function of Berry curvature. So that's something where there is a physical singularity. The Berry curvature is singular, and that is a physical singularity. In the cases we're discussing here, the Berry curvature is entirely smooth. There's nothing singular in the Berry curvature. But in this 2D space, if the Chern number is non-zero, then you can't have a smooth vector potential.
Okay, thanks. And I'm so sorry, but one last question, quick one. You mentioned the Berry curvature would be a Dirac a delta function, in which case, are these the same as the lattices you mentioned earlier, or is it just entirely different?
Mathematically, you can make it. There's a mathematical connection between the two. Here we're thinking in reciprocal space, this would be a a pi vortex, not a 2 pi vortex. This would, sorry, this, so the vortex I was mentioning before would be like a Berry curvature of strength, a delta function of 2 pi. A delta function of 2 pi, that's what I meant by a sort of invisible vortex, or the Dirac string. So a Dirac string I could think of as a tube of flux with one flux quantum or 2 pi of phase that's concentrated down to an infinitesimally narrow region, but because it's a 2 pi flux, it's invisible. And so the vortices I was mentioning before, you could think of as being delta functions of weight 2 pi. In the Dirac case, actually what you have are 2 Dirac points, and the 2 Dirac points are of strength, pi and pi, and the two together give you pi and minus pi. It's well, it depends how you split them. We'll hear from Tillman, I think, about splitting Dirac points. But in the Dirac point, it's really a pi or a minus pi, depending on how you how things are split for the Berry curvature. And whereas the sort of invisible, and so those are individually, they are visible and have physical consequences. Whereas the vortices I was mentioning before are like 2 pi Dirac delta functions, which are physically invisible.
Okay, thank you very much for your patience.
No, thanks for your questions. Okay, let me, so I wanted to, so I was saying that we don't need to restrict the system by any symmetries, but that symmetry does play a role in determining whether or not the Chern number is non-zero, and in particular, this is a time reversal symmetry. And so here, I just wanted to mention it because it will come up later if I get to other parts of the lectures. So in time reversal symmetry, the way we, in classical dynamics, for example, the way we understand time reversal symmetry is we say that we have time reversal symmetry if the equations of motion are, so if the equations of motion are invariant under t goes to minus t, momentum goes to minus momentum, and position goes to position. So it's not. And this, if we were to think about say, Hamiltonian dynamics, where we'd say that dr by dt is dh by dp, ph is the classical Hamiltonian, and dp by dt is minus dh by, sorry, these should be partial derivatives, dh by dr, dh by dp, then this means that the Hamiltonian has to be an even function of momentum. H of r and p is h of r and minus p. And that's essentially true for non-relativistic particles. If there's no magnetic fields, there's no vector potential. So that's now in quantum mechanics, at least for a spinless particle, this, of course, all goes through in the same way. And the result that you'll find is that the quantum Hamiltonian, H, let's put a hat on it, has to be real. So it's H is equal to its complex conjugate. And the way, so that the time reversal is related to complex conjugation. And the way you can to derive that, or to see that this matches what we had in the classical case, is that we know that the complex conjugation of the position is just the position, but the complex conjugation of momentum is, if we write the momentum operator, h bar over I d by dr, then we get a minus sign. So it's this complex conjugation that reverses momentum, and so time reversal is related to complex conjugation. And one can show, but I'll leave it as an exercise, that if the Hamiltonian is real, then you can show that the Berry curvature omega at wave vector q is equal to minus the Berry curvature at minus q. And so the Chern number, which is 1 over 2 pi times the integral of this Berry curvature over the surface of the Brillouin zone, has to vanish. So if we want to make bands for spinless particles that are that have non-zero Chern number, then we need to break the time reversal symmetry. So it's not that we need to have symmetries in order to define the Chern number. If we want to get, it's that we have to make sure that we break time reversal symmetry if we want to have something which has got a non-zero Chern number. So that's a key feature, and of course that's key for any implementations. And there are various models that are canonical models for the Chern number that have been implemented in cold gases. So a central one is the Harper model, or sometimes called the Harper-Hofstadter model, which is a tight binding model on a square lattice where you have hopping, but where the hopping along some site, instead of just being some real amplitude j, has got some phase here, e to the phi ij, between sites I and site j. And if we have this phase, then, well, that phase, of course, now breaks time reversal symmetry, unless it can all be removed by some unitary transformation. We have a complex Hamiltonian, and so we're breaking time reversal symmetry. And physically, this can, in the Harper model, you set up these phases so that there's a net uniform flux of phi AB through each of the plaquettes. And this model is well known to have this very complex fractal structure of the Hofstadter spectrum, where the energy spectrum breaks up into many bands depending on the precise value of this flux. So this is, so I'm not going to talk through implementations because I think Tilman's going to talk about these things, and Monica perhaps as well. But this has been done using laser-assisted tunneling. The laser, the things have to be set up so that you're imprinting these phases, and introducing these phases is using a situation where you're breaking time reversal explicitly by the way in which you're modulating your laser beams or shaking a lattice in a way that's time reversal it's not time reversal invariant, so you've definitely broken time reversal symmetry. Another way in which this is implemented is in so-called synthetic dimensions, where we really have a one-dimensional system of sites along this direction x, along here, but you use Raman coupling to couple between different internal states. And if we just plot those internal states in the synthetic direction m, then you have a two-dimensional lattice, or in this case a ladder, a three-leg ladder, where by using tuning the phases on these Raman couplings between the internal states, one can imprint these fluxes. There's another classic model is the Haldane model, which I'm sure Tilman will talk about, which is a two-site system. It's a unit cell of two sites, A and B, shown here, A and B. So one unit cell contains just one A site and one B site, and then this tunneling J on this honeycomb lattice gives us the graphene lattice, which has got these gapless points, gapless Dirac points. But as Haldane pointed out, by putting in this direct coupling from A to A, then you can, with phases, again breaking time reversal symmetry, so that with we have these phases of phi AB appearing, then we've broken time reversal, and you can get a non-zero Chern number. And finally, I want to mention that another way in which you can do this is to use internal states in spin orbit coupled lattices. So this is, again, it's like this. We've got some internal states which we're coupling with lasers, but now we really make everything vary, not just in one dimension, but in two dimensions. So there's a real physical, spatial, two-dimensional lattice. It's just that the states at each point in space can be address states of the different internal states of the atom. And there, one can generate Chern bands either in rather deep lattices by making models where there's a tight binding model with fluxes, which look a bit like these Harper models or Haldane models. Or one proposal that we came up with was in shallow lattices, where which have a nice feature that you can get a rather high flux density and rather flat bands, which may be useful for getting strongly correlated phases. So I mention these just to make the connection to cold gases, but I'm not going to talk through them because Tillman will do that, or others will do it. But I want to pick up on this Haldane model and say how you can understand the Chern number in a simple way in models of this type, where we have just two sites in the unit cell. That is where there are just two bands in the system. So if we have two band models, like for example the Haldane, then we know we can write our Hamiltonian, and everything is uniform, so we have a Hamiltonian that's wave vector Q. We can write it as, well, as before. We can write it as hz minus hz x, hx minus I hy, hx plus I hy, so minus h of q dot sigma z, where the difference now is that we haven't constrained any chiral symmetry, so we're allowed to have a non-zero hz. Okay? So we have something that means that, well, we have everything as before. The energy spectrum is plus or minus mod h of q. U minus of q is the state that we get from minimizing the energy here, and of course we can think of this on a block sphere. So take the block sphere, we can think of the state as being some particular direction where the mean value of the spin is aligned with the local field h of at that value of q. So yeah. Now, if we so I want to make one comment that to make connection to a question that Leo asked yesterday that I didn't answer correctly, or didn't pick up on, which is, imagine we have the Brillouin zone, and we take some path in wave vector, so that the block state changes in some way. So of course what it means is on this block sphere, the state we're in will wander around and come back to where it started from, because we came back to the same state Q as before. And we can compute the line integral, or the integral of the let's say we compute the Berry phase that's picked up, q dot dq around this loop, and this, which of course is equivalent to the curl, to the integral of the Berry curvature over the entire surface, and we can interpret that in terms of what's happened on the sphere. That this is traced out some solid angle. I call it omega s for solid angle to distinguish from the Berry curvature, which I also wrote as omega. This is some solid angle. And the result from Berry's paper is that for a two-level system, which is equivalent to spin a half, the phase, if you pick up, is 1/2, because it's spin a half times this solid angle. So spin 1, it would be the full solid angle, spin 2 times solid angle, and so on. But for 1/2, it's half the solid angle. So in particular, in the case of where we had winding around the equator, then that's the solid angle traced out is half of the sphere, so it's 2 pi. So half of that is pi, so you get a pi of Berry phase from winding once around the equator. And well, if you don't wind at all, then it's 0. So this is precisely the point that Leo was making yesterday, and it's a very helpful way to interpret what the Berry phase is for these two-level systems. Now, it also is a useful way to interpret the Chern number, because if we have we have our two-dimensional Brillouin zone, and now we extend this contour to be over the entire system. It doesn't have a boundary, it just runs over the entire system. So this what we have on the sphere, either it shrinks down to a point and the solid angle traced out to 0, or it has to cover the sphere and in a way that leaves no boundary, and it could cover the sphere an integer number of times. So the Chern number is, well, it's the integral of the, let me just get the factors right. So the Chern number, remember, was defined as 1 over 2 pi times the integral of the Berry curvature over this. So it's 1 over 4 pi times the solid angle swept out, and of course it's covering the sphere once as a solid angle of 4 pi. So this is just the number of times the sphere is wrapped. So we can for these two-level systems, and just for this two-level system where we have this simple pictorial representation of the state in terms of this 3-component unit vector, then the Chern number is this number of times we have a wrapping. And so just to have some picture in mind, this is meant to represent a periodic system. Well, it's periodic because at the boundary everything's pointing up, but the spin or the local block vector goes from up to down. It visits every point on the surface of the sphere, but it does it in such a way that it wraps the sphere once. And so this would correspond to a system or a situation with a Chern number that's 1. Okay, so the way that let me just think, right. Okay, yeah. So the way that appears.
That's a quick question.
Yeah, of course.
Cool. So I don't mean to take us too far off topic, but I kind of wanted to ask about whether or not that picture in this 2-band model changes at all in any interesting way for quadratic touchings instead of the linear ones.
For quadratic touchings?
Yes. Yeah. So I think, let's see. If I'm not mistaken, the way you've written this Hamiltonian would describe like Dirac points, where the dispersion away from the singularity is linear. But if you have, good.
Yeah, no, I was going to say that there are no band touchings here at all. So so that's an important point that I should emphasize. That here this is, here we're still considering the situation where there are bands, sort of different bands which are distinct and they don't touch each other, and we're just going to characterize the properties of one isolated band. If there's a band touching, that's the situation where we're not able to define a topological invariant for the isolated band itself. Maybe we can do something for the pair of bands that touch or so on, but it's a requirement, and it's part of of what we're looking at now is that we really want to think about situations where we have an isolated band and uniquely at each point in wave vector there's a unique wave function UQ for the lower band here, UQ minus, which is well defined and separated from other states by some gap. So I don't want to be thinking about band touchings at all here. I want to just consider the properties of this isolated band. Does that answer the question, or remove the question, or clarify what's being considered?
I think his internet may have dropped off. At least his video went blank there.
Okay.
Maybe he can
he can come
back on. I mean, I guess also in the simple picture you had of the block vector on the sphere, to even define that block vector as an eigenstate uniquely requires that H is non-zero, right?
Right.
And I guess that's the condition that there's no band touching.
That's right. Yeah, that's right. Yeah. So there's H of non-zero to. Yeah. Thank you. Yeah. So I just wanted to sketch what this looks like in the Haldane model. So the Haldane model, remind you, was this story with the honeycomb lattice, 2 sites in the unit cell. And because of the because of the honeycomb lattice geometry, the Brillouin zone in that case, just sketch it, roughly QX, QY, it takes a form where it's the Brillouin zone is a hexagon, and there are two special points at this corner, which I'll call Q plus and Q minus. And if you only have the this coupling J from A to B, and so on, and not the second nearest neighbor coupling, so we just have this honeycomb lattice like graphene, then the band gap vanishes precisely at those 2 points. So you have 2 points, Q plus and Q minus, where there's an exact gap.
Did we all lose Nigel or just me?
Yeah, we lost him.
Yeah,
Okay.
I also lost him. So I think it's Nigel, yeah. But
So we'll wait for him if anyone wants to, you know.
Yeah, Kaden, go ahead, explain it to us.
Yeah, so there's a picture of a circle here and there's a little dumbbell. If anyone did want to discuss things, now's a good time. So Charles, I think you were logged off when I made a comment, so I'll just repeat my comment, which is that H of Q that he had written down, it's always non-vanishing in the case he was looking at there. So there's no band closing. And if you think about that block sphere picture, then so the fact that we can draw that block sphere means that the eigenvector is well defined for that problem. Otherwise, we wouldn't know which direction the eigenvector was pointing. And so we were actually requiring that H was non-zero and that there was no gap closing just to be able to uniquely define a block vector.
I guess the comment I would make is, and maybe it echoes what Nigel was also saying, it's kind of not useful to introduce the vector potential, or maybe it causes some confusion, because for these problems, there's if you think of it as in a sphere, there's a monopole inside that sphere. And so if there's a monopole inside the sphere, divergence of B is non-zero. Once the divergence of B is non-zero, then there's no single valued vector potential that you can introduce. And so because of that, these issues arise with the you can't really use Stokes' law to convert it to a line integral. And to Charles' question, I mean, it's just two different problems. They're superficially look quite similar in that it's still a 2x2 system. There's still a effective external, Zeeman field, H of Q, dot sigma, but they're just two different problems. In one, magnitude of H of Q never vanishes. And in the other, the one you asked about where there's band touching, H of Q has vanishes, and therefore there's a singularity in the vector in the Berry flux in the region that you're interested in, corresponding to the place where the H of Q vanishes. So just two different problems.
Also, it appears Nigel's back, so you can jump in and share whatever you want.
Yeah, hi. I'm trying to share my slides, but I don't see it myself. Does anybody?
We don't see it either.
Okay, let's try again.
Okay, we see you.
Okay.
Looks like it's working now.
Something coming? Yeah. Okay. Can you see?
Yep.
Yep.
Okay. So I was I'm not sure where I got to when it cut out, but I was saying that if you have the hold-in model with only the nearest neighbor tunneling, so that's the same as graphene, then the bands touch at these points Q plus and Q minus, which are these special points in the Brillouin zone, these two particular points. But whenever you put in this further neighbor hopping, you open up some gaps, and you can it's convenient to expand around these 2 points. So we write Q is approximately Q plus or minus plus some Q tilde, again, expanding around these points. And around each of these points, there's a Hamiltonian H of Q tilde, which is approximately, well, there's some velocity or some coming from the tunneling rate, plus or minus Qx tilde sigma x, just Qy tilde sigma y, plus, and then there's some Hz, which is different. In general, it's different in around the plus point or around the minus point, times sigma z. Now here, this is a bit like the expansion that I did before for the SSH model. There's difference is that here I've never written down what the Hamiltonian is that we're expanding. So please just take my word for it that when you expand around these points, that you get a structure of the matrix which looks at this type. Now it's consistent with the story what I said about the Dirac case. So if we turn off that further neighbor tunneling and only have the nearest neighbor tunneling, and that corresponds to wiping out this last sigma z term, and then you see that when Qx tilde and Qy tilde are both 0, the Hamiltonian vanishes. That's to say that there's really a band touching, and those are the 2 Dirac points. And what this Hz is doing is to open up a gap. And what Haldane realized was that you could open up those gaps in a way that you could get a churn band. And what I want to do is to show this in order to just sketch what the block vector is doing around each of these points. So around one of these points, around say Q minus, we might have some point where Q tilde is 0, so there would be a Dirac point. But there, let's say that Hz minus is less than 0. So we tuned our parameters so that this correction coming from the Haldane model here is negative. Then the block vector will point in the plus sigma z direction, which I'll denote by a little point for the arrow coming up. But in the other directions, if I'm in, let's say, if Qy is 0 and Qx is non-zero, then I get minus Qx sigma x. So I get something that points in the, let's call this the x direction. On this side, it's the minus x direction. And if we run around this, then you'll find that around this, what was a Dirac point, but it's now opened up, you have something where the block vector is rotating. Its xy component does a vortex, and its sigma z component points out of the plane. And similarly around Q plus, I won't go through it in quite as much detail, but let's say there we can, if we choose that if the plus point is greater than 0, then the block vector points in the negative z direction. So I'll write that as a plus sign rather than a point. And then as we go around, in this case, the in-plane component has a vortex of the other sense. Its angle increases as we go around in a clockwise sense, whereas in this case the angle decreased. And taking these 2 things together, you get a net. It wraps the block vector wraps the sphere once, and you get a churn number of 1. So the magic or the beautiful aspect of the Haldane model is to be able to take these Dirac points and to, in one case, to make the block vector point up, and the other one make the block vector point down. And if you do that, you get a topological band. Whereas if they both point the same direction, then you don't. So I think, in view of time, what I think I'll do is, so I wanted to go on to talk about physical consequences, but I'll never do that in the few minutes remaining. So what I maybe do is to make an aside, which is to make connection to something that at some level looks a bit different, but it turns out to be identical. I do this because it's something I like myself, because I learned something from working through it, and it relates to so-called optical flux lattices, which I referred to earlier, which we thought about as being formed from spin orbit coupled lattices. So that spin orbit coupled. So this is something I worked on in 2011, and then subsequently with Jean Dalibard in various different papers. But so we have a spin orbit coupled lattice, which I had written down before. We had some momentum operator. There's an identity matrix. This identity operator, it acts on internal states, and there's some V of R, which is some coupling which now couples internal states. And here, what I have in mind is that we might have two, let's say, two spin states of an atom, which are coupled by some two photon transition, or are dressed. There are two photon dressings, which can give rise to light shifts of the two levels and coupling, coherent coupling between the two levels. So we get dress states, which are described by some coupling V, which is really, well, in this case, it would be a 2x2 matrix acting in the space of these two internal states. So this is something that, the light fields, they vary in space on the scale of the optical wavelength, and they imprint some couplings locally on the atom, which puts it into some dress state, or which are superpositions of these different internal states. And the case I want to consider is where we have the mass of the particle goes to infinity. So we can basically neglect its kinetic energy. It just sits at whatever point in space we care about, and we can think about adiabatic motion. So we have some V of R, some local dress states, the local eigenstates of this coupling, N of R. So this is another, it's ripe for thinking about in terms of Berry phases. If we, now we have Berry phases in real space. If we think about starting in one of these levels, let's say the lowest energy state, N of 0, let's say it's the lowest energy state at some point in space, and we make some loop and bring it back, then we know that we'll pick up a phase, and the phase that we'll pick up is given by the line integral of the Berry connection, which is now a Berry connection in real space, related to the variations, the spatial variations of the light field that's dressing the system. And the nice thing here, which I believe Ian Spielman will talk about later in this meeting, is that this will give us a real space Aharonov-Bohm effect. So it can give us a synthetic magnetic field. So we get an Aharonov-Bohm effect. So we get a synthetic magnetic field, which is just given by directly given by the Berry curvature in real space, curl of whatever vector potential we get out of this. So this is just like what we said before, but now we're making a real magnetic field in real space. We're thinking real space rather than reciprocal space. But based on this idea, with Jean Dalibard, we had lots of fun thinking about ways in which you might be able to make a lattice that would give you a net flux in a unit cell, and therefore would look like like bands with Landau levels and so on. And we came up with various schemes, and they're all very pretty, and they work when they work really nicely. But there's one of them that I just want to sketch here, which involves two-level system as before. So here are my two levels. And they're dressed by light beams, which are low frequency, red and blue, and there's a set of beams that run in plane, which are linearly polarized, and then one that goes perpendicular to plane, the blue, the higher frequency one, which is circularly polarized. And you can look at this and immediately say it breaks time reversal symmetry because it has circular polarization. And so this thing breaks time reversal symmetry because sigma minus is different from sigma plus under time reversal. So we've set up something that breaks time reversal. It could give us churn bands, and it can give us some effective magnetic field. But and it all works. It's beautiful. It's wonderful. But the one thing I want to point out is like there's a really a neat connection that I hadn't realized until later, and this is that we should really think about this in reciprocal space. Right? You know, whenever you experimentalists set up an optical lattice, it's really better to think about what's happening in giving 2 photon kicks to atoms. You're really imprinting, 2 photon transitions which give momentum kicks to atoms. So let's think about what happens in momentum kicks here. So we have let's say we start in the plus state, and we've got a set of beams which are, the in-plane ones are all at 120 degrees to each other. The red ones here are running in the plane, and then there is the blue one is pointing out of the plane. So it's like this. So let's say we start in the plus state, and we have a 2 photon transition where we absorb from the blue and emit in the red. So then we can get transitions which are basically emitting in these directions, momentum kicks in reciprocal space. So this is reciprocal space. We get momentum kicks, and where we end up in the other state, minus. But and we can. So, is there a question?
I think they're muted now. Nigel, you also muted yourself.
Okay, thanks. So we can do this again and again, and each time we flip which state we're in, and we build up a honeycomb lattice in reciprocal space. Yeah. Okay. So that's in reciprocal space. We're making like a graphene lattice in reciprocal space. But then we also have another thing we can do, which is we can just do 2 photon transitions on these reds. So we can absorb one of these and emit into the other. And the momentum transfers are such that you get these transitions between, and if you do that, you don't change the state of the system. That's just a 2 photon transition where you might go up here and come back down, or go up here and down. They're sort of dressings of the individual levels. So what you get is that you get couplings which are the next nearest neighbor ones. So actually what this lattice is doing is it's generating precisely the Holdian model in reciprocal space. And the fact that the Holdian model can have a Berry curvature in momentum space means that, in this case, well, the opposite of reciprocal space is back in real space. So here we get a real space Berry curvature, which was our magnetic field. And the situation where the Holdian model gives you a churn band, so let's say churn number 1, means the magnetic field is such that there's exactly 1 flux going through each unit cell. So C equals 1 band means you get 1 flux per unit cell. So in fact, this, once you realize this, then actually there's a very beautiful way in which you can think about constructing flux in real space by viewing it as being like a churn band from some tight binding lattice in reciprocal space. And since really the lasers give you the control as to what you're imprinting in reciprocal space, you can think about what lattices you want to make in reciprocal space and what phases you want to impose on the different transitions in order to deduce what real space Berry curvature you get, and therefore what real space magnetic field. So this was a bit of an aside, but all of the mathematics is, because we're not really making a band here, we're just making magnetic field in real space, but all of the mathematics is equivalent, and actually one ends up looking at the Holdian model again, even when you have a laser configuration that looks like this. Okay, I think since I'm out of time, I'll stop there. I'll run to my summary slide, which is just to show you what I have covered and what I haven't covered. So I basically, what I got through is talking about the Chern number and the Berry curvature and focusing on two-band models. And I think it was really useful to have the questions to keep to clarify this. And I hope that some of it has made an impression. Next time I'll go on to talk about physical consequences and topological insulators and superconductors. But so I'll stop there and I'll see you again tomorrow. Thanks.
Very nice talk. So questions, everybody?
Yesterday, you briefly mentioned, I guess, that for the Zach phase, it's only quantized when in the presence of symmetries and it's not otherwise. And for the Chern number, it seems just like the 2D analog of it, but you said it has to be quantized. So what's the difference there?
Well, well, I mean, the Chern number, I guess the Chern number is, I mean, the quantization of the Chern number is really just a reflection of the fact that we're dealing with quantum mechanics and states that have got this 2-pi phase ambiguity. And the existence of this 2-pi phase ambiguity in quantum states is completely universal and makes no reference to what state or what Hamiltonian or we're thinking about. So once you have that 2-pi that phase ambiguity and
Somebody's sorry, just make sure you're muted.
Yeah, Nigel, I unmuted you, but I muted everybody else.
Yeah, so once you so that's a very particular and special feature that if you're in 2 dimensions with this 2-pi phase ambiguity, then you have this quantized topological invariant. Now the Zach phase, like other phases which are symmetry protected, is something that's just much more delicate. You know, but by itself, it's not based on, you know, it's not based on such a robust feature. It's based on the feature of a subset of states, you know, that you're looking at not all possible wave functions in the Hilbert space, but a restricted subset of them. And that restricted subset, you know, it's restricted in different ways, and the different ways it's restricted can give rise to different things which might look like the Zach phase or might look like some other invariant. But you're really, I think that the key distinction is that the Chern number is based on this universal feature of quantum mechanics and the existence of the complex Hilbert space, and the other is related to properties of a subset of the states, and therefore it's not held by the general class. That's a lengthy way of saying that one of them does not require symmetry and the other one does require symmetry. But I think that it's fair that it's pointing out the key role that the U1 phase plays in quantum mechanics, and whereas in the other cases we're restricting, we're restricting the state. We have to put some restriction on what states we allow the system to deform between.
We have
another. Can I just add to this? Maybe, I mean, maybe Nigel can comment. Isn't one way to connect them and therefore see the distinction, Nigel, is, for the Chern number, you're integrating over the full surface. It happens to be a torus, but you're integrating over a full closed surface, and therefore, like in the Dirac problem, naively, there's no pi because it has to be invisible Dirac string. While in the Zach phase, if you extend your space beyond, in the way you described it, the way I pointed out, then you integrating over only half of a sphere, you're integrating over open surface with a boundary that's non-trivial. So if you want that to be some fixed number, you have to demand some, you have to impose a symmetry to keep that curve pinned at the equator.
Yeah, no, that's yeah, for the two-level case, I think that's a great way to visualize it. That you're in general, that integral can take whatever, there's no constraint on what that integral is.
Right.
Okay? You can envisage running over states in the Hilbert space where that integral is not quantized, and so you need to restrict yourself to a subset of the Hilbert space. And in that case, in the two-level system with the block sphere, we can think about it as the equator, and that gives us that's a nice way to visualize the restricted Hilbert space that we're working. Yeah.
So there's a question from Jaren. Go ahead and ask.
Please.
So my question is related to last slide that you discussed, your paper. If you can go there.
Yeah, let me see if I can. See if I can get. Hold on. Here. Yeah.
Curious is like, how did you actually come up with the honeycomb lattice in the reciprocal space? Is that related to how you put the lasers together in the real space?
Yeah, thanks for the question. So yeah, so the sketch, so these lasers, these red lasers, they're all in the 2D plane. They're running at 120 degrees to each other. So the sketch that I have here is meant to represent in the plane that we've got lasers which are all 120 degrees to each other. So that's sort of setting a sort of triangular threefold symmetry. And the blue one is out of the plane, so it's also sort of rotationally symmetric, isn't it? But so the way I came up, yeah. So let me just yeah. So the way I came up with this. So for the bonds I put in blue, that corresponded to say absorbing from the blue laser, which gives me no momentum kick in the in-plane direction, and then emitting one of these red photons. So emitting, let's say in this one, if I emit in this one, I get a kick to the right and I end up over here. So I end up this one. So good. So these blue ones are basically the reverse of these three in-plane red lasers, because the momentum kick on this nearest neighbor coupling is coming from the emission or absorption of these red photons and the absorption or emission of these blue photons. And that gives us kicks in these three directions at 120 degrees. And when we concatenate all of those, we get the honeycomb lattice. So that's the honeycomb lattice. And it has two sides per unit cell because there's a plus and a minus. So it's a two-side honeycomb lattice in reciprocal space. And you get that, I mean, this laser configuration is used regularly. The Hamburg group has made an enormous use of this setup and do some very beautiful configuration studies. But if you think in reciprocal space, it's actually a honeycomb lattice in some sense. But then these dotted red lines, those are coming just from the red lasers themselves. So I could absorb, let's say I absorb this one, absorb this photon, and then emit this one. And then I get a momentum kick in that direction, a vertical momentum kick, and that would be this line, or this one. Okay, and the other, basically the other pairs of absorption and emission give me the other two second nearest neighbor couplings. So those fill in all of the second nearest neighbor couplings. And I didn't talk about phases, but take my word for it that, that the things are set up so that you get phases which give you a band that's topological, and therefore you get a real space magnetic field.
It's very interesting. I have one more question. It's a clarification question. So the here on this the transition, the red arrows, red transitions, are those like connecting the G plus and the upper manifold there, or is it somewhere in the between? I wasn't really sure.
Yeah, it's detuned from the upper manifold, because we want to we're just looking at the second order process. It's detuned from it, so there's no, so we eliminate the higher levels, and we only think about this as an effective 2-photon coupling. So the only degrees of freedom we include are the G plus and G minus, but it is indeed, you're using sort of near resonant coupling to these upper levels. Now, in order to get a general feature for these spin-orbit coupling problems, is that if we actually want to have processes where we have state-dependent magnetic fields, spin-dependent, so there's a difference in spin up and spin down or transitions between them, then you have to be, the detuning cannot be too big. It has to be of order or within the fine structure splitting. And so this detuning, there's also the detuning, it has to be within the fine structure, or you won't get any state. This matrix V will just be a scalar, and you just get a scalar usual optical lattice, which is the scalar lattice. We need the vector component of the light shift, and so the detuning needs to be cannot be too large.
Okay, thank you very much.
Sure.
So Botao?
Yeah, sorry, since time is limited, but I'm afraid I have a stupid question. So since we are talking about the chain number, so which are the integral of the Berry curvature across a closed surface, and the value can be quantized. I mean, but by saying quantized, it can be 0 or non-zero. But for the non-zero, we can interpret it as, let's say, some numbers, integer number of monopoles inside this closed surface. But my question is that I would take, let's say, for the Hofstad model. So let's say for different value of flux, the lowest band may have different chain numbers, right? So my question is that so for by varying the value of fluxes, so we have different chain number or different monopoles inside the closed surface. So my question is that why does this happen? So where are those monopoles from? I mean, so maybe it's just too stupid. It just happens like this. But do you have an intuitive argument for that? Simply by varying the value of flux, I have different chain numbers, and also different chain numbers will this also repeat reproduce the phases of the lowest Lambda level. So, right, I think chain number equals 1 and 2 have apparently different physical consequences.
Yes, so I don't think I have a very intuitive answer for where do those monopoles come from, or I think it does relate to the particular model. In the cases in the case that I just described for the optical flux lattice story, there I know some limits in which we can think about how to basically imprint. Basically, you can imprint the Berry. How in those cases we can imprint the local Berry curvature around plaquettes in reciprocal space. So by phases and by putting particular phases in reciprocal space, but that's very much engineered, and it's not. I don't think it answers the question you want of where the monopoles come from. And one thing to say, as one goes from one region to another, like here we've got a set of bands which have got churn number 1, and those you can understand as being this sort of. So this is the Harper model at small enough flux that square lattice looks like a continuum, and we can make an approximation that it's like Landau levels, and Landau levels are
Yes.
Chern number 1. But indeed, you're right that here the lowest band has got Chern number 2. And in fact, if you're around 1/3, this has got Chern number 3. And around, so that's around 2/3, I think. But if you're around P over Q, then close to it, you get Chern number Q, magnitude of the Chern number, something. So you can, in this structure, if you zoom in more and more, you can get large Chern numbers. How does the monopole change? I mean, nothing ever happens smoothly. There's something very discontinuous in going from one of these to the other, and you can see, of course, that to go from the region we've got Chern number 1 to where it looks like Chern number 2, you've gone through a whole lot of states which are states have been broken up in lots of complicated ways, and gaps have collapsed, and the number of states in that lowest band has changed as well. It's not, the unit cell has changed, so there are very significant changes in going from here to here. It's not something that can smoothly happen. The actual size of the unit cell changes as we change the flux here. So there's no sort of smooth continuity or between these different regions. So I don't think I can give a very good intuitive interpretation other than saying that one is constructed. I mean, there are limits in which you can understand how you've made states which look like Landau levels or even printed Berry curvature. But like I said, that to me, I have rather technical views of how that happens. And of course, if you've imprinted a net Chern number that's non-zero, then we know there has to be a monopole inside. And so it's a very indirect way of answering it or viewing it. So I'm afraid I can't help, I think, with the intuition you're looking for.
Yeah, that's why I said it's actually a stupid question. But thanks a lot.
Not stupid.
Yeah.
I just there may be another way to look at it, but that's not the intuition I have myself.
Yeah, thank you.
Thanks.
So maybe we're running a little late. It's already 1/4 and I want to make sure we have enough time to grab a coffee or lunch. So maybe I'd suggest to leave further discussions tomorrow. We'll have, and hopefully, I'm not sure if Nigel will be able to join us, but I hope he will. Well, he'll be giving a talk, but we'll also have the discussion afterwards. So maybe we can leave that further questions for that, or just discussions on Discord. Does that sound okay with everybody? I just want to make sure there's enough time before Tillman's talk at 11.
Good.
Caden, are you there?
Yeah, I'm here. You got the thumbs up from me for sure. Mhm.
Yeah. So maybe let's just break here and let's reconvene. It's maybe in 15 minutes, like at 11:05, we'll aim to start.
Great.
Okay. Thank
Great
you.
talk. Thanks, Nigel.
Thanks.
Thank you.
Bye.